Good morning or good afternoon to everyone who is joining us today. My name is Cícero Franco da Silva. I am a researcher at the Paulista University UNIP in São Paulo, Brazil, linked to the La Proma Research Group. Today, I will present the work entitled Integrating Emergy Synthesis in the Sustainability Assessment of School Infrastructures. This work was co-authored together with Professor Cecilia Almeida, as well as Professors Biagio Gianetti and Feni Agostinho. The problem: school buildings represent a major investment of natural, economic, and social resources. However, when we carefully analyze the existing literature on sustainability, most school assessments tend to focus on pedagogical indicators or energy certifications related to the operational phase, and for the most part, they overlook the material and energy costs involved in constructing these structures. This creates a significant blind spot. The construction phase, which is the crucial moment when materials like concrete, steel, glass, as well as labor and equipment are all consumed in order to bring the building into existence, still remains even today rather poorly qualified. And when labor is accounted for, it typically refers to institutional staff members such as teachers and administrators rather than construction workers, the people who actually build the building. The objectives. This study addresses three specific objectives. First, to quantify the total energy embodied in the construction of a three-story basic education school building in São Paulo, Brazil. Second, to explicitly account for construction labor by professional category utilizing unit energy values that are derived from wages, a methodological contribution that so far has not yet been applied to educational buildings. And third, to compare our results with previous studies of Brazilian educational buildings and discuss implications for school construction policy. What is emergy? For those who are perhaps less familiar with the method, emergy synthesis was originally developed by Howard Thomas Odom in the field of systems ecology. Emergy, spelled with an M, is the total solar energy directly and indirectly required to generate a product or sustain a system. It is expressed in a single unit, the solar energy joule equivalent, or SEJ. The great advantage of energy accounting is that it allows for the integration on the same analytical basis of natural resources, industrial materials, energy, and human labor. Everything is converted by means of unit energy values. The UEVs are precisely calibrated to a global reference value of 1.2 times 10 to the 25th power SEJ per year, ensuring consistency. This provides us with a truly genuine measure of the overall environmental cost. Not just the energy used, not just the money spent, but the complete and total biophysical investment that is behind a product. Methodology. The system boundary covers only the construction phase, from the project's conception to the delivery of the building. The building is a three-story school with a reinforced concrete structure, including classrooms, administrative and common areas, a multi-sports court, sanitary facilities, and circulation corridors. Physical data were obtained through on-site surveys and the creation of architectural drawings in CAD. Therefore, the data collection process was direct. We identified 14 construction stages and qualified 14,705 labor hours distributed across professional categories, from laborers and masons to electricians, plumbers, and civil engineers. For labor energy, we applied the Emergy GDP approach using the Brazilian ratio of 8.46 times 10 to the 11th power SEJ per Brazilian real. Importantly, we adopted the employer's perspective, meaning the total cost of hiring, including mandatory social charges like INSS, FGTS, and payroll provisions, which adds approximately 53% to the gross salary and more fully reflects the social investment needed to maintain each worker. It thus adds a compensation and valuation of time beyond what is effectively employed in direct labor. The UEVs for construction professionals range from 9.86 times 10 to the 12th power SH per hour for laborers and masons to 5.41 times 10 to the 13th power SH per hour for engineers and architects, a 5.5 times difference between the categories. Results: the total embodied energy of the building was 4.364 times 10 to the power of 18 SEJ, applying an annual depreciation rate of 4%, consistent with an accounting useful life of 25 years. The annualized energy flow is 1.746 times 10 to the power of 17 sej per year. The composition is highly concentrated. Concrete, plaster, and masonry enclosures account for 90% of the annualized energy across the 3 floors. 1,358,011 kilograms of concrete were carefully quantified before any waste was considered, rising to 1,629,613 kilograms with the application of the 20% waste factor. Civil construction labor is the second component, with 6.14% resulting from the 14,705 hours distributed across 14 professional categories. All other materials, steel, ceramics, glass, fiber cement tiles, wood, and plastics individually contribute less than 1.31% each. Regarding sustainability indicators, the renewability fraction is approximately zero, confirming total dependence on non-renewable resources during the construction phase. This is expected and informative, not a limitation of the method. Methodological contribution. I want to highlight what we consider the central methodological contribution of this work. Previous emerging studies of educational buildings in Brazil, including Almeida and colleagues from 2013 on the UNIP Indianapolis campus, and Oliveira and colleagues from 2018 on the Federal Institute of Southern Minas, accounted for human labor. However, in both cases, the labor category referred to institutional employees, teachers, administrative staff, and support workers. The construction workers who built these buildings were never individually quantified. This study fills that gap by providing salary-differentiated UEVs for 14 construction categories, distinguishing the energy cost of a bricklayer from that of an engineer or an architect. This approach is transparent, reproducible, and consistent with the theoretical framework proposed by Udiati and Brown in 2014. We recommend its adoption as a standard policy in future building energy analysis, discussion, and implications. Our results align with and expand upon previous Brazilian studies. The consistent finding across all reviewed works is concrete dominates the construction energy of educational buildings. At UNIP Indianapolis, concrete accounted for 52% of the energy. At the Federal Institute of Southern Minas, 57%. And in our study, 90%. The higher share in our case reflects a more restricted system boundary. We analyzed only construction materials, without operational flows or equipment, not a fundamentally different building. 3 implications for public policy emerge clearly. First, construction energy is large and irreversible. The 4.364 times 10 to the 18th power SH invested in this building will depreciate over 25 years at 4% per year. The most effective sustainability action is to maximize the occupancy of existing school buildings before investing in new construction. Second, in the design phase, material substitution offers real leverage. A 10% reduction in concrete volume through structural optimization could reduce the total annualized energy by approximately 9%. Third, our sensitivity analysis showed that a variation of approximately 20% in all key parameters produces only around 7.8% change in the total results, confirming that the results are robust. Conclusions. In summary, this study applied emergy synthesis to a 3-story basic education school building in São Paulo, Brazil. The main results were as follows. The total embodied energy, which amounted to 4.364 times 10 to the 18th power sej, or alternatively 1.746 times 10 to the 17th power sej per year. Concrete accounted for 90% of the annualized energy. Civil construction labor represented 6.14%, accounted for individually in 14 professional categories for the first time in the educational energy literature. The renewability fraction was approximately zero, confirming a total dependence on non-renewable resources. The main limitation is the scope. This study covers only the construction phase. Future work will extend the accounting to the operational phase. Staff, energy, water, and consumables, enabling a complete energy assessment of the school's life cycle as a biophysical and educational system. Acknowledgements and closing. I would like to thank the La Proma Research Group at UNIP for the institutional support and the co-authors, Professor Cecilia Almeida and Professors Biagio Gianetti and Fanny Agostino, for their contribution throughout this research. The full article, data tables, and the inventory of unit energy values are available upon request. Sincerely, I am available for any questions. Thank you very much for your attention.